Hello and welcome to part 3 of the Orbital Yacht Club presentation. For the past 35 years, I've been sharing a vision of permanent human settlements in space with anyone who will listen. However, I always preface the vision with the statement, one of these days. A few years ago, I realized we have everything available to actually do it now. Not in a small tin can environment with all the complexities of microgravity, but in a spacious platform with all the utility, security, and luxury we've come to expect in our lives. Be sure to like us on YouTube, post an awesome comment, and share it with your friends and family. Let's make this thing go viral so it will get the attention it deserves. This is where we show you how to build an orbital yacht club. The engineering criteria includes making a commercial space station with private yacht docking, including Earth, Mars, lunar, and microgravity zones. It has to be spacious and affordable for the purposes of science, manufacturing, and vacations. And it should have the ability to be transported to other orbits, including the Moon, Mars, and the asteroid belt. Usually when you go from the design phase to the engineering phase, you have to increase complexity and decrease functionality. While engineering the Orbital Yacht Club, the reverse happened. We decreased the complexity while increasing the functionality. Instead of using trusses, we used cylinders for the structure of the wheel. This provides a stronger structure and creates space for controlled environments. Using this design, the blue outer ring provides 40 docking ports for space yachts, each with 600 square feet of private space and 1,400 square feet of public space, for a total of 80,000 square feet of Earth gravity. The red module in the middle ring provides additional structural support while also providing 25,000 square feet of Mars gravity. The yellow inner ring provides 8,000 square feet of lunar gravity and serves as the transfer hub to the microgravity modules that have a total of 16,000 square feet of space. The purple and green spokes provide elevators to travel between the different zones, but when I realized we don't need 8 elevators, it dawned on me to use the other 6 spokes for farming fresh food. This provides 86,000 square feet for farming. We will show how we can build the Orbital Yacht Club with all of these features for $250 million per docking port spread out over 5 years at $50 million per year. This is very affordable for any multi-billion-dollar government agency, corporation, partnership, or individual. Looking at the side view shows how the microgravity modules are attached perpendicular to the ring structure. Here's one module of the Earth gravity ring. This shows the side view and the end view of the cylinder. It's 8 meter tall and 16-meter long with 4.5-degree bevel on each side and a docking port in the middle. There's a crawl space 3 foot high for mechanicals, including plumbing, electric, and AC ducts. The first floor has an 8-foot ceiling, and the second floor has a 12-foot domed ceiling you can see on the end view. There's on the end view, you can see there are airlock doors to isolate each module. In the event there's an air leak on any module, then the remainder of the station can maintain the integrity of air pressure. You can see how the angle of the walls are used to maximize space for the spiral staircase on this side and a countertop with cabinets on the other side. Here's the first floor plan showing the docking port where you can climb up from your orbital yacht. Then you can go into either cabin, each with a private bathroom for a total of 600 square feet of space. You can also go through this door into a 200 square feet public hallway that travels the entire circumference of the Earth gravity ring, similar to a hotel. The spiral staircase leads to the second floor. The second floor has 1,200 square feet of open space to be finished out for dining, shopping, medical facilities, etc. 40 of these modules are joined together with airlock doors to form the outer toroid of the space station for 80,000 square feet of gravity. This is more than enough room to support 320 people living on the station. Here's the side view of one module of the Mars gravity ring. By building this ring 38 with a 38-meter radius, it provides 38% of the gravity produced on the 100-meter ring. This is by design because Mars gravity is 38% of Earth gravity. This module is a 7-meter diameter cylinder that is 15 meters long with an 11.25-degree bevel on each side. The crawl space is 2 feet high for mechanicals. The first floor has an 8-foot ceiling with 600 square feet of floor space. The second floor has a 10-foot domed ceiling with 1,000 square feet of floor space. This picture shows the domed shape. 16 of these modules are joined together with airlock doors to perform the middle toroid of the space station for a total of 25,000 square feet of Mars gravity. This is more than enough room to learn, train, and play in Mars gravity. Here's the side view of one pair of modules for the lunar gravity ring. By building this ring with a 17-meter radius, it provides 17% of the gravity produced by the 100-meter ring. This is by design, since lunar gravity is 17% of Earth gravity. Each module is 7 meters in diameter, that is 7 meters long, with an 11.25-degree bevel on each side. There's only one floor with 500 square feet of floor space. This picture shows a lava tube, which is where some people think we should build our habitats on the moon and Mars. By decorating 1 or 2 pairs of modules like this, we could use it for training or tourism. 8 pairs of modules are joined together with airlock doors to form the center toroid of the space station, for a total of 8,000 square feet of lunar gravity. Additionally, this ring acts as the transfer hub between the gravity modules and the microgravity modules. There's a docking port on the bottom to attach to the elevator spokes while in lunar gravity mode. Then there are docking ports on the side to attach to the microgravity modules while in microgravity mode. Here's the side view of one of the microgravity modules. These are not rotating with the rest of the station, therefore they are continuously in microgravity. This module is a 7-meter diameter cylinder that is 15 meters long with a docking port to attach to the lunar gravity ring when it's in microgravity mode. This picture of the inside of the proposed Axiom Hub 1 could be similar to the interior of some of these modules. There are 16 modules for a total of 16,000 square feet of gravity. Here's the top view of one of the elevator modules. These are used as spokes to travel between the different gravity zones. This module is 6 meters in a 6-meter diameter cylinder that's 14 meters long. The elevator in the center has a 4-meter diameter, which is very large for an elevator. It's made similar to a Tesla automobile with the battery in the floor, then dual electric motors drive 4 wheels up and down tracks in the shaft. For safety, the emergency brake automatically engages unless power is on to release it. There is a 1-meter wide staircase spiraling around the elevator shaft. Although ours will probably not be made of glass, this is a great picture to easily see the inside, outside, top, and bottom of the elevator. There's a total of 10 modules to make the 2 purple spokes for large elevators. Here's a top view of one of the farming modules. These are used to farm fresh food. It has a 2-meter diameter open cage elevator in the center to access each farming ladder. Then there are 2-meter deep shelves that glide on rails to create space to access the entire shelf. There's a total of 30 modules making up 6 spokes that can also access the different gravity zones. Since the shelves do not need to be 8 feet apart like a floor, we can get an average of 12 layers per module. Multiplying that by 240 square feet of farming space per layer to get a total of 86,000 square feet for farming. Since the elevator modules are 6 meters in diameter by 14 meters long, they fit inside the Mars, Lunar, or Micro G modules that are 7 meters in diameter by 15 meters long. And these fit inside the Earth modules that are 8 meters in diameter by 16 meters long and are used as the payload fairing during launch. With this architecture, we've reduced the number of launches by a factor of 3, from 120, one launch for each module, down to only 40 launches, each with 3 modules, greatly reducing the total launch cost. Let's take a look at the mechanics of the artificial gravity. The Earth and Mars rings are always spinning together at 3 rotations per minute. The elevator spokes connect the Earth and Mars rings. The lunar ring is connected to a truss with train rails. Then a maglev train engine can rotate the lunar ring at 3 rotations per minute and align with each elevator spoke for docking to transfer between the lunar ring and the elevator spokes. When the docking ports on the bottom are released from the elevator spokes, the maglev engine can slow down the lunar ring like this to align with the microgravity modules. They attach using the docking ports on the side, and doors open like a subway train or a transport you might see at a large airport to allow people to transfer between micro and lunar modules. The center microgravity module hub is always stationary and connects to the elevator spokes with its own maglev train system to maintain 0 rotations per minute. Once everyone is transferred in and out of the microgravity section, the lunar ring can undock and begin spinning at 3 rotations per minute again to dock with the elevator spokes. This is what the interior of the station looks like. Every module has an airlock door to isolate each one in the event of an air leak. If you're visiting the Mars ring and want to go to the Earth ring, you simply step into the elevator and go down to that level. To go to the lunar ring, you can simply go up like this. Then a ladder drops down so you can access to the lunar ring. You simply climb up the ladder. At regular intervals, the docking port will release like this, and the lunar ring will slow down to align with the modules, the micro G modules. Then these docking ports will attach. And doors will open up to be able to travel between the micro G and lunar rings. Now let's talk about the farming modules. Notice the farming layers are very close together near the top. That's so you can grow food that doesn't grow very tall, like lettuce, cucumbers, or strawberries. Then you can travel down to the open cage elevator to the medium height shelves where you can grow tomatoes, pineapples, or potatoes. Finally, you can go down to the tall shelves where you can grow taller crops like corn or wheat. Similar to pipelines, the modules are steel cylinders attached with bolts. Each roll of the Formula 301 stainless steel used is 60 inches wide. They're fabricated to the proper length, radius, and 2-inch rails on each side. 16 panels are welded together to form the cylinder. Each module is fully sealed on one end with airlock doors. When joined together in orbit, they form an airtight seal with 1 atmosphere of pressure. An interior coating of propylene glycol with Kevlar fibers, just like that used in self-healing tires, permanently repairs small leaks. Since the floors are curved, struts are manufactured into the modules with the proper radius for first and second floors of each module and attached to the steel rails. This completes the manufacturing of the module on Earth. Then it's transferred to low Earth orbit, where the floor joists are attached to the struts. Finally, the floor, ceiling, and wall panels are attached to the joists. This is the Falcon Heavy that can lift 140,000 pounds of payload to low Earth orbit. This payload fairing is the same one that's used on the Falcon 9. To further reduce launch cost, we will use the Earth gravity module as the payload fairing by attaching it with a collar and a nose cone. One of the micro, lunar, or Mars modules fit inside the Earth module. Then one of the elevator sections fit inside of that. With a combined weight of under 100,000 pounds, there's still room for the ancillary equipment required to assemble the modules in orbit. Therefore, it takes a total of 40 launches to insert all the materials required for assembly in low Earth orbit. I would like to believe we can use the Crew Dragon as the nose cone to further reduce launch costs, but SpaceX hasn't responded to my request for information. This concludes part 3 of the presentation. Check out part 4, where we will show more engineering, the budget to build the Orbital Yacht Club, and some competitive analysis. Be sure to like us on YouTube, post an awesome comment, and share it with your friends and family. Let's make this thing go viral so we can get the attention it deserves. Thanks a lot, and have a great day.